Beneath Europa's frozen surface lies an ocean larger than all of Earth's seas combined. Could it hide alien life in the dark? Today we'll dive into the science and the possibilities of this icy moon. If you enjoy the journey, please like, subscribe, share, and let us know your thoughts in the comments. Thank you for watching. Now let's begin. Europa is a small, bright world that circles Jupiter in a steady path. It belongs to the family of 4 large moons that travel with the giant planet, a group that also includes Io, Ganymede, and Callisto. Europa is a little smaller than Earth's moon, with a width a little over 3,000 kilometers, and its pull of gravity is gentler than the pull a person would feel on our own moon. Its path is close to circular and takes about 3.5 Earth days to complete. Like many distant moons, it is tidally locked, which means the same face always points toward Jupiter, while the other face looks out toward the stars. This locked spin keeps the view of Jupiter nearly fixed in Europa's sky, and sets a slow rhythm for light and shadow on the ground. The moon's shape is nearly spherical, with only gentle departures caused by the steady pull of the planet and by the moon's own rotation. The surface reflects sunlight strongly, which gives Europa a pale, clean tone when seen from afar. No thick atmosphere surrounds it. The horizon is sharp, the sky is black, and the ground keeps its heat poorly in the long day and in the long night. Jupiter guides Europa's movement with quiet persistence. The moon keeps time within a 3-body resonance. For every orbit Europa completes, the inner moon, Io, completes about 2, and the outer moon, Ganymede, completes about 1/2. This 1 to 2 to 4 pattern prevents Europa's path from becoming perfectly circular. Instead, the distance between Jupiter and Europa grows and shrinks by a small amount each circuit. The repeated change in distance makes the planet's pull rise and fall in a gentle cycle. These cycles flex the moon not with sudden jolts, but with slow, regular strains that press and release the outer shell and the interior again and again. The result is a world that appears calm at the surface while it undergoes steady, controlled stress through each lap around the planet. From space, Europa looks smooth. The globe is crossed by long lines that curve, branch, and rejoin in wide loops. Many of these features appear as double ridges with a central trough, like 2 low walls standing on either side of a narrow lane. In other places, the surface seems to have been cut into rafts that drifted, slightly rotated, and then froze in their new positions, leaving a quiet mosaic of blocks with rough edges and offsets. Large impact craters are rare, and those that do exist are shallow. The scarcity of deep scars and the crispness of ridges suggest that the surface renews itself on timescales that erase old marks. The overall impression is one of gentle relief rather than high peaks or deep basins. The ice plains lie nearly flat, broken, mainly by the long dark bands and occasional rounded swells. The environment far from the sun is cold. Sunlight at Jupiter's distance is weak, and the ground temperature on Europa remains far below the freezing point of water through both day and night. Because there is no thick blanket of air, winds do not blow, and sound does not carry well near the surface. The topmost layer of ice is hard and brittle. Tiny projectiles from space arrive from time to time and pepper the ground with small pits. Charged particles trapped in Jupiter's magnetic field sweep past and strike the surface, changing the chemistry of the uppermost skin of ice and darkening some lines and patches. Even so, from a distance, the world remains bright, a pale sphere with fine markings. A closer look at the long lines reveals patterns that hint at how the shell behaves. The paired ridges likely form when the surface pulls apart along a crack, allowing material from slightly deeper, warmer levels to rise into the gap and then freeze when it meets the cold exterior. Repeated episodes build 2 low walls flanking a narrow groove. Elsewhere, bands of darker material occupy lanes where the surface once widened and fresh ice filled in the opening. In several regions, rounded domes and low spots appear, forming a subtle texture that suggests slow motions within the shell. None of these structures require fast events. They are consistent with steady stress, small temperature changes, and the passage of time in a rigid layer that can crack near the top and flow very slowly at depth. Europa moves through a harsh belt of radiation. Jupiter's magnetic field traps energetic particles that race along invisible paths and bombard the ice. These particles can split water into hydrogen and oxygen, and can drive other simple chemical changes. Some products escape and some remain trapped in the topmost layers. Salts and simple oxidants can accumulate at the surface and may stain the ridges and bands with a darker tone. The radiation does not carve the features, but it does alter the thin skin of ice that lies open to space. Over long periods, these processes refresh the chemistry of the outermost grains, without adding noise or motion to the quiet landscape. The length of day and night follows the orbit. Sunrise comes slowly. The sun climbs arcs and sets over a period of about 3.5 Earth days. Long shadows creep across ridges and troughs. When darkness returns, the surface cools again toward the deep cold of space. No breezes stir frost. No clouds pass overhead. The only visible motion on most days is the drift of light and shadow, and on rare occasions the brief flash of a distant impact. The slow pace matches the locked spin and the steady orbit, and it allows the surface to hold its calm appearance without interruption. Measurements of Europa's size and mass show that it is layered inside. Dense rock and metal concentrate toward the center, making a core and a rocky mantle. Above that dense interior lies a very broad outer layer made of water in different forms. Near the top water is solid ice that behaves like a brittle crust when pulled or squeezed. Deeper down, warmth and pressure allow the same substance to deform slowly over time. These basic layers help explain the surface shapes. A brittle outer shell supports sharp fractures and sliding blocks. A warmer layer beneath can carry slow, gentle changes that lift, spread and heal the surface over long intervals. The details of each boundary need not be drawn here. It is enough to note that a layered interior fits the observations and gives context to the quiet pattern seen from orbit. Europa's position so close to Jupiter creates regular alignments. At times, the moon slips into the planet's shadow, and sunlight fades until the orbit carries it back into day. At other times, Europa's own shadow crosses the cloud tops of Jupiter as a sharp, round mark that glides across swirling bands. These events repeat with dependable timing and do not change the cold ground by very much. They do, however, underline how near the moon lives to its parent planet, and how strongly the planet's presence shapes the moon's experience. Across the globe, the balance between smooth plains and patterned fractures is consistent. Long, gentle arches run for great distances, while darker bands trace old lines of weakness. Rounded spots and low domes add a quiet topography that does not call attention to itself from afar. No tall mountains rise. No deep valleys cut across the plains. The record is one of strain recorded with modest relief. The result is a world whose face tells of slow repeating forces rather than sudden violent change. Seen from far away, Europa is simple, a pale sphere with fine marks. Seen up close, it is intricate, a shell etched with ridges, bands and sliding blocks. Both views describe the same place. The first view speaks of calm. The second view speaks of slow change. In both, the setting endures. Europa turns with its locked rotation circles Jupiter with steady timing and holds a bright cold surface that reflects the faint sun. No storms sweep the ground, no haze softens the horizon, and no rivers carve channels. The landscape waits in silence, and the great planet fills a fixed place in the sky. Europa's surface is a quiet atlas of ice written in long lines and low forms. From a distance, the ground looks smooth and bright, yet a closer view shows a shell laced with cracks that arc branch and rejoin, and with bands of darker material that run great distances before fading into the plains. Many of the most persistent features are double ridges. Each consists of two low walls separated by a narrow groove. The pair holds a nearly constant width as it travels across the terrain, bends around older marks, and crosses other pairs without losing its identity. The walls rise only modestly above the plains, but at low sun they draw sharp shadows that make their shape clear. Within the central grooves lie streaks of darker ice and fine rubble, and in places small knobs sit along the crests, as if built by repeated gentle additions of frozen material. The paired ridges often assemble into bundles that keep nearly parallel spacing for long distances, so that the landscape displays corridors of twin lines running like cords laid upon a pale sheet. Beyond the paired ridges lie broader lanes that are flatter and darker. These bands keep sharp margins, and their interiors carry fine longitudinal striations. They appear at many scales. Some are only a little wider than a typical double ridge, while others spread to widths of several kilometres and run for many hundreds of kilometres without strong changes. The band floors sit close to the level of the adjacent plains, and their tones shift toward brown and red against the blue-white of clean ice. Along their edges the ground may step down by a small ledge, or may feather into the plains with only a faint change in brightness. Narrow thread-like fractures often occupy the centres of these bands, as if the lane preserves a memory of the crack that first opened the ground. Not every place holds long order. In several regions the tidy fabric of lines gives way to rafts of broken ice that look as if they cracked free, rotated by small angles, and drifted aside before the landscape froze again. These blocks keep the same internal ridges and bands seen in the surroundings, so the eye can trace a line through one block, lose it in the darker hummocky fill, and then find the same line within the next block at a slightly different angle. The margins of the blocks can be abrupt with short scarps that drop into the rough fill. The fill itself shows knobby texture and a darker tone with no tall peaks and no deep hollows, only irregular mounds that rise and fall gently. The arrangement resembles a jigsaw that has been shifted and then set not by haste but by slow movement that left the pieces nearly intact. Elsewhere, the eye meets chains of short curved cracks linked end to end. Each segment bows one way and then the next, so that the chain traces a gentle zigzag across the plain. The arcs keep nearly constant length and spacing and sweep through older features with little loss of form. In some places, two chains run side by side for a while before joining again, making a ribbon of paired curves that persists for long distances. Where such chains cross double ridges, small lozenges and lens shapes appear at the intersections. These arrangements give the surface a woven look without strong relief. Scattered nearly everywhere are low domes, shallow pits, and round spots with modest rise or fall. The domes lift gently with slopes so slight that they barely disturb the horizon. The pits are equally gentle, their floors lying only a little below the surrounding plain. Some spots show a bright core with a darker ring. Others carry a shallow dimple at the top, as if their centres sag just enough to catch shadow when the sun stands low. Their diameters span from several hundreds of meters to a few kilometers, and they often gather in loose fields rather than stand alone. The forms do not demand a single cause here. They simply present a recurring punctuation upon the broader pattern of lines and bands. Impact scars exist but are not abundant. The largest fresh crater on the visible face spreads pale rays for great distances, laying narrow streaks of bright ejecta over the older landforms. Most other craters are modest in size and shallow. Their rims are subdued, and their interiors have relaxed toward level ground. In several cases, the floors show darker material that may include grains altered by radiation mixed with local ice. The relative scarcity of large deep craters allows the fabric of ridges, bands, chains, domes and pits to remain legible across very broad areas. Colour on Europa is restrained. The broad plains keep a high reflectance and display the blue-white of clean water ice. The line's bands and disrupted fills hold richer tones that trend toward brown and red. Spectral evidence gathered from orbit points to salts and simple oxidants mixed into the ice in these darker areas. Some observations match hydrated sulfate salts. Other observations align with chloride salts that, when altered by radiation, take on yellow and brown hues. The precise mixture likely varies from place to place, and the outermost grains of ice are modified by charged particles that split water and drive simple chemistry. The result is a thin skin whose colour and texture shift gently across the globe, with stains focusing within grooves and bands while the plains remain bright. The two hemispheres show a quiet contrast. The hemisphere that trails the direction of motion appears a little darker overall, as if it receives a greater dose of charged particles and fine debris that the Moon sweeps up along its orbit. The leading hemisphere is a little cleaner and brighter. Near the poles, the widest bands are less common, and the surface shows finer linework and more frequent low spots and domes. None of these differences are stark. They are subtle tendencies that lend the global map a mild asymmetry without breaking its unity. Relief across the globe remains modest. No mountain chains rise to break the horizon. No deep canyons cut the plains. Most ridges climb by several tens of meters at most, and most troughs lie only a little below the surrounding ground. Even within the disrupted regions where blocks have shifted and turned, the height changes are small compared with their breadths. The surface records strain and motion, without building tall piles or deep holes. It is busy with lines and textures, yet remains gentle in shape. At the smallest scales that images resolve, the upper skin of the ice shows granular textures and faint coatings of frost tucked into shadow. Tiny pits mark the places where micrometeoroids struck and flashed a little ice into vapour. The skin that lies open to space has been altered by radiation for a thin depth, so that it looks a touch darker and slightly rougher where the flux is strongest. There is no drift of loose dust, no ripples shaped by wind, and no dunes to store memory of a breeze because there is no thick air to move grains. Instead, the finest textures change by slow sintering of ice grains, by gentle fallout of fresh frost, and by the patient work of radiation upon the topmost layer. Light controls how these forms reveal themselves through the long day. Because the day lasts for about 3.5 Earth days, the sun lingers at low altitudes for many hours, and shadows move slowly across the ridges. As the sun climbs, contrast shifts from shadow to colour, and the dark bands and stained grooves show more by hue than by shape. When Europa passes into Jupiter's shadow, the ground falls into total night. When it emerges, sunrise brings back the plains first, then the darker lanes, then finally the fine threads within the grooves. The result is a surface that remains calm, even as it displays a wealth of detail, a frozen shell, whose patterns can be followed without hurry across a bright, cold world. Beneath Europa's bright shell lies a layer that does not show itself directly. The surface is ice, the sky is black, and there is no thick air to carry signs upward. To learn what rests below, observers read the surface gently, weigh the moon, measure how it responds to fields and forces, and watch for brief traces of vapour above the horizon. Each method speaks in a quiet voice. No single clue is enough on its own, but together they point toward a broad body of liquid water hidden under the ice. The case builds step by step from properties that can be measured at a distance. A first step is to consider Europa's overall mass and size. The Moon is a little smaller than Earth's moon, yet its mass and volume together give an average density, that is lower than solid rock but higher than pure water ice. This combination fits a structure with a dense interior made of rock and metal and a very thick outer layer made of water in different states. Such layering does not prove the presence of liquid water, but it sets the limits. There is enough water to form a deep shell. If part of that shell is warm enough, then within the pressure range inside Europa it can be liquid. The question is whether such warmth and such a layer actually exist now. A strong piece of evidence comes from Europa's behaviour inside Jupiter's magnetic environment. The giant planet carries a large magnetic field that sweeps past the Moon and changes with position and time. When a changing magnetic field passes through a conductive layer, it drives electric currents. Those currents in turn create a secondary magnetic field that instruments can detect. Measurements made during close passes show that Europa carries an induced magnetic signature that varies in step with the changing field of Jupiter. The simplest way to make such a signature is to have a global layer near the surface that conducts electricity well. Salt water is an efficient conductor at the temperatures expected within Europa's outer shell. Rock near freezing temperatures conducts poorly. An ocean of salty water several tens of kilometers below the surface extending around the globe explains the strength and timing of the induced field in a direct way. The conclusion does not rest on a single pass but on repeated crossings that map out variations, which then match calculations for a spherical shell of conductive liquid beneath ice. The surface itself shows patterns that are easier to make if the outer ice floats upon liquid. Long cracks curve in chains of arcs that change direction systematically across the globe. Such chains form naturally when a brittle layer rides on a mobile substrate and is pulled and pushed by tides. The double ridges that dominate the landscape also favour a shell that can open slightly along a fracture, admit warmer material from depth, and then close again as the material freezes. The disrupted regions that look like rafts separated by darker, rougher fill suggest that sections of the shell once broke loose, rotated by small angles and drifted before they set again. These motions do not require fast flow. They do require that at some depth the shell can decouple and allow relative movement, which is most simply achieved if ice lies upon liquid water. Subtle changes in Europa's shape under the steady pull of Jupiter provide another window. A body that is entirely solid resists deformation, whereas a body with a floating outer shell allows small but measurable flexing as forces change through the orbit. Observations are consistent with a shell that yields a little over time rather than a rigid crust welded to a solid interior. In the same way the surface supports or fails to support long loads can be used to estimate the thickness and strength of the shell. Some ridges sag only slightly over their widths, which points to an ice lid that can carry its own weight across moderate spans. At the same time, very broad features do not maintain high relief, which points to a layer that can flow slowly at depth and level the ground over long intervals. Together, these patterns fit a scenario in which a cold, brittle lid rides atop warmer, softer ice, and the warm ice in turn sits above liquid water. Resurfacing rates tell a consistent story. The scarcity of large, deep impact craters implies that the present surface is not ancient. Old scars have been softened, partly buried or removed. On a small airless world made only of cold rock, such smoothing would be slow. On Europa, the more rapid renewal suggests that the upper shell has been rearranged from below by additions of new ice and by slow flow at depth. Liquid water that moves heat efficiently can assist such renewal by keeping the lower shell warm and weak enough to creep over long timescales. Chemistry on the surface also hints at communication with depth. Spectral measurements reveal salts mixed into the darker bands and along some ridges. On their own, these salts could come from many sources, including alteration by radiation at the surface. However, certain mixes of chlorides and sulfates and the way they stain and hydrate fit a picture in which brines are brought upward from below, exposed briefly to space, and frozen in place. If the ice shell is cracked down to depth, and if liquid water beneath carries dissolved minerals, then small amounts of that briny water can be drawn upward, along fractures during opening events, and then left within the crack to freeze. Over time, the cracks can build paired walls and darker in fill as repeated episodes add layers upon layers. Short-lived traces above the surface add a further thread. On several occasions, telescopes have recorded narrow columns of water vapour near Europa's limb. Some detections are strong, others are marginal, and several searches find nothing at all. The picture is intermittent. Even so, the events that are most secure suggest that plumes of vapour rise from the surface at certain locations and times. A straightforward way to make such plumes is to vent water from within the shell or from the liquid layer beneath, which then flashes into vapour in the vacuum of space. The total mass involved in these events is small compared with the global shell, but their existence supports the view that volatile material moves upward, at least occasionally linking the hidden interior to the open sky. Models of heat inside Europa show that several sources act together. Heat from the decay of long-lived radioactive elements in rock supplies a steady base. On top of that, slow flexing of the moon by Jupiter's gravity adds energy within the ice and within the underlying water. If heat production and heat loss balance in the right way, an internal ocean can persist for very long periods beneath an insulating lid of ice. If the balance changes, the lid can thicken or thin. The present patterns on the surface are most easily matched if the lower shell is warm enough to deform, and if a liquid layer lies below to decouple the shell from the rocky interior. The depth to liquid and the thickness of the liquid layer remain uncertain. Estimates based on different lines of evidence favour an ice lid that is at least several kilometres thick, and could be several tens of kilometres thick with a liquid layer beneath that may be tens of kilometres deep, and perhaps much deeper in places. These threads do not rely on a single type of observation. They include mass and size magnetic induction surface structures, small changes in shape under tidal forces, chemical stains in ice, rare vents of vapour, and the logic of heat flow. No one line rules the others. The strength of the case comes from how they meet. A global ocean of salty water beneath an icy shell explains the induced magnetic field in a direct way, and allows the surface to behave as observed. It provides a mobile boundary that helps renew the landscape at a rate that keeps the terrain young and modest in craters. It allows salts to rise and freeze within cracks. It allows occasional vents to reach the sky. Without such a layer, each observation would need a separate, more complex story. With such a layer, the stories join. The result is a calm, coherent explanation consistent with the measured properties of a bright, cold moon that holds a hidden sea beneath its plain of ice. Heat inside Europa arises from steady flexing driven by Jupiter's gravity, and that heat keeps water liquid beneath the ice. Europa's story begins with its orbit. The moon circles Jupiter in a path that is slightly stretched rather than perfectly round. A resonance with Io and Ganymede maintains this small eccentricity, so the distance to the planet grows and shrinks a little during each circuit. Because Europa keeps the same face toward Jupiter, the direction of the stretch changes as it moves along its path. The body deforms, relaxes, and deforms again in a rhythm set by the orbital period. Each cycle performs mechanical work upon the interior. Resistance within materials converts part of that work into heat. The process is called tidal dissipation. It is not a single event, but a steady action that repeats without hurry and adds energy to the system over long spans of time. Tides within a solid body are slow changes of shape under a changing gravitational field. Europa lengthens a little along one axis while it shortens along another, and the orientation of that pattern shifts with orbital position. Layers respond according to their properties. Brittle ice near the surface carries stress by cracking when the strain is high. Warmer ice at depth flows gradually. Liquid water can move to accommodate change without breaking. Rock in the mantle deforms only slightly. Where resistance is strongest and shear is focused, more energy is lost as heat. The distribution of heating depends on the structure of the shell. A cold, thick lid is stiff and stores elastic energy. It releases that energy where fractures focus stress, which may favor heating beneath belts of ridges and bands. A thinner or warmer lid is softer and yields more broadly spreading dissipation over wider areas. If an ocean lies beneath the shell, the ice is decoupled from the rocky interior. So much of the tidal work occurs within the ice itself and within the ocean. If the ocean is patchy or thin, stresses may couple more directly into the rock. These alternatives matter because they set where heat is produced and how it moves upward. Radiogenic heat adds a steady base. Long-lived radioactive elements within rock release energy through slow decay. By itself, this base may not support a deep ocean beneath a thick lid, but it reduces the burden that tides must carry. The combined budget of radiogenic heating and tidal dissipation must balance the loss of heat through the shell if liquid water is to persist. If input exceeds loss, the base of the shell warms, melts and thins. If input falls short, the shell cools and thickens. The ocean persists when the two sides remain in balance within the range set by the properties of ice and water. Heat escapes upward by conduction and by slow overturn of ice. Conduction is the direct transfer of heat through a material from warm parts to cold parts. Cold ice is a good insulator, so conduction alone allows only a small heat flux. If the shell is thick and the temperature difference between its base and its surface is large, buoyancy can drive convection. In that case, warmer, softer ice at depth rises in broad plumes, while cooler, stiffer ice near the surface sinks in wide lanes. Convection transports heat more effectively than conduction, and can carry warm material upward until it nears the brittle lid where motion slows, and heat must again cross by conduction to the surface, and then radiate to space. Tidal heating interact with this pattern of heat loss. A region that becomes slightly warmer softens, dissipates more tidal energy, and warms further until a new balance is reached. A region that becomes slightly cooler stiffens and dissipates less. Such feedbacks may help explain why some belts of fractures and bands are more active than others, and why the map of surface fabric varies with position. The ocean itself participates in the tides. As the shape of the moon changes, the free surface of the water adjusts and pressure gradients drive currents along the base of the ice. Where water moves past the ice, friction warms the boundary. Narrow passages and roughness can focus flow and create small hotspots. Even gentle currents can dissipate a significant total power if the ocean is global and deep. Pressure and composition change how ice melts and freezes within the shell. For ordinary ice at modest pressure, the melting point decreases as pressure rises. That trend makes melting a little easier at depth. Dissolved salts lower the freezing point further. Briny water can therefore remain liquid where pure water would freeze. As ice grows at the base of the shell, crystals tend to exclude salts and leave them in the remaining liquid, which makes the brine more concentrated. Thin layers of dense, salty water can then persist in pockets and along interfaces. Such layers conduct electricity well and may help explain magnetic signatures, and they also influence how and where heat is released because salty water resists freezing until lower temperatures are reached. At great depth, water may transform into high-pressure ices denser than liquid water. Whether such phases exist within Europa depends on the total thickness of the water layer. If the ocean is very deep, A mantle of high-pressure ice could sit between the liquid and the rocky interior, limiting direct contact between water and rock. If the ocean is more modest, liquid may rest upon rock and allow hydrothermal circulation. These alternatives influence where heat is produced and how chemicals move, but both still allow significant tidal dissipation within the shell itself. The supply of tidal energy endures because the resonance with Io and Ganymede persists. These moons exchange energy and angular momentum through gravity in a way that prevents Europa's path from relaxing to a perfect circle. The resulting small eccentricity keeps flexing active. If the resonance were to fail, eccentricity would decay, flexing would fade, and heating would drop. With the resonance in place, gentle cycles continue for long times, and provide a stable source of internal power. Other inputs are small. Charged particles that strike the surface alter chemistry but do not deliver meaningful heat to the interior. Sunlight is too weak at Jupiter's distance to influence the deep shell. Impacts deposit energy locally but are rare. The controlling terms are the slow work done by tides and the steady base from radioactivity countered by the insulating effect of ice, and by whatever convection develops within the shell. Taken together, these processes yield a quiet balance. Jupiter's gravity supplies a repeating mechanical input. Europa's eccentric orbit turns that input into cycles of stress. Resistance and flow within ice, water, and rock convert part of each cycle into heat. Radiogenic decay adds a constant flaw. Conduction and convection move the heat upward. If input and loss remain in balance, a global ocean persists beneath a bright frozen plain. The process is patient rather than violent, regular rather than abrupt, and sufficient to maintain a hidden sea under a cold sky far from the sun. Europa's surface chemistry is shaped by the constant interaction between frozen water salts and the radiation environment that sweeps through Jupiter's magnetic field. The ground is bright, dominated by water ice, but stains of red-brown and yellow mark ridges, bands, and disrupted regions. These color changes are not decorative accidents. They are records of chemical change carried by salts drawn from the interior, altered by the bombardment of high-energy particles, and frozen into place across the plains. Understanding these traces requires looking step by step at the ingredients and the processes that mix them. Water ice is the bulk material. Its crystalline structure reflects sunlight strongly and gives Europa its high brightness. Pure ice absorbs little in the visible range, so the background tone is clean and pale. However, pure ice is also chemically simple. To make the darker stains, other compounds must be present. Observations with instruments sensitive to infrared light reveal absorption features that cannot be explained by ice alone. These features match hydrated salts molecules that include ions of sodium, magnesium, or sulfate bound with water. The precise mixture varies from one location to another, but the evidence is consistent with brines that have been exposed to space frozen and then irradiated. One way to bring salts to the surface is through fractures. When the brittle lid of ice opens even slightly, pressure differences can drive liquid from below upward. That liquid may carry dissolved minerals from interaction with rock or from concentration within the ice shell itself. Once exposed to the cold, the water freezes quickly, leaving salts behind in a crust within the fracture. Repeated cycles of opening, intrusion, and freezing can build the paired walls seen along ridges, and can leave dark bands of salt-rich ice between them. The composition of these deposits is not uniform because the chemistry of the liquid and the degree of radiation alteration both vary. Radiation plays a central role. Jupiter's magnetic field traps charged particles that move rapidly along field lines and bombard Europa's surface. Energetic electrons and ions strike the outermost layer of ice and break molecules apart in a process called radiolysis. When water molecules split, hydrogen escapes more easily than oxygen, leaving oxidants behind. These oxidants can combine with salts or with other molecules to create new compounds. The process alters both color and composition, darkening the surface and creating materials that would not form in the deep interior. Over millions of years, the bombardment penetrates to depths of several tens of centimeters, ensuring that the upper skin is thoroughly altered. Spectra of the stained regions often match mixtures of sulfate salts and radiation products such as sulfur dioxide or hydrated sulfuric acid. Sulfur itself may come from Io, the innermost large moon of Jupiter, which erupts with volcanoes that release sulfur compounds into space. Some of this material becomes trapped in Jupiter's magnetic field and rains down upon Europa, mixing with the local ice and brines. The result is a surface environment where materials from inside the moon and from the Jovian system beyond it combine. The balance between supply and alteration can vary across the globe. The trailing hemisphere, which faces opposite the direction of motion along the orbit, receives a heavier flux of energetic particles and dust. Its bands and ridges are generally darker and more strongly altered. The leading hemisphere is somewhat cleaner, with fresher ice exposed more often. Poles differ from equatorial regions because of the geometry of magnetic field lines and the angle of incidence of incoming particles. Yet all regions share the common traits of ice salts and radiation products mixed in varying degrees. Small-scale texture affects how chemistry appears. Where fractures expose fresh ice salts may be more concentrated along the margins, and thin coatings may look darker against bright planes. Where blocks of shifted, rougher surfaces hold more irradiated material, deepening their color. Domes and pits may contain frozen brines with compositions distinct from the background. Because the process of irradiation is continuous, any new exposure will gradually darken over time until it blends with its surroundings. The timescale of this change depends on flux, but it is measured in thousands to millions of years short compared with the age of the moon. A separate line of evidence comes from tenuous atmospheres above Europa. Instruments have detected faint oxygen and hydrogen escaping from the surface. This escape is explained naturally by radiolysis. When water molecules are split by energetic particles, hydrogen, being light, can escape more easily into space, while oxygen can linger in the near environment or become trapped in surface grains. The presence of this faint oxygen envelope confirms that chemical change at the surface is not only staining the ground but also creating products that reach above it. The chemistry therefore links the hidden ocean below the ice shell, the surface, the radiation environment, and the space around Europa. One can step through this chain slowly. Deep water interacts with rock or with concentrated brine pockets in the ice and dissolves salts. Fractures open under tidal stress and small amounts of that water rise and freeze. Salts are trapped in the solid ice near the surface. Charged particles strike and split molecules, creating oxidants. Sulfur from Io adds to the mix. New compounds form, darken and stain the ridges. Oxygen is released, some trapped in ice, some lost to space. Each step is simple, but together they create the observed surface chemistry. The energy driving this cycle is external radiation combined with internal motion. Without tidal, flexing fractures might not open to allow brines upward. Without Jupiter's magnetic field, radiation chemistry would be weaker and stains less intense. Europa's distinct appearance therefore depends on both its place in the Jovian system and its own internal dynamics. The exact mixture of compounds remains uncertain. Some models favour magnesium sulfate as a dominant salt, while others favour sodium chloride, the same salt common in Earth's oceans. Laboratory experiments show that sodium chloride, when irradiated, takes on a yellow-brown hue similar to patches observed on Europa. If this interpretation is correct, then the ocean may be closer in composition to Earth's sea than once thought. On the other hand, the presence of magnesium and sulfur compounds suggests different chemistry. Both options remain consistent with the data, and the debate illustrates the limits of remote sensing across such distances. Regardless of the exact salts, the interaction between water minerals and radiation builds complexity in a place that otherwise looks quiet and static. The importance of surface chemistry extends beyond appearance. If oxidants are created at the surface and later mixed downward through cracks, they can provide chemical energy to the hidden ocean. Life as known on Earth requires not only liquid water, but also sources of energy. If Europa's surface continually manufactures oxidants and salts, and if those products are delivered to the ocean, then the ocean receives a steady supply of potential fuel. The rate and efficiency of this delivery remain open questions, but the principle is simple. Surface chemistry under radiation is not just decoration. It is a potential engine for habitability. In summary, the chemistry of Europa's ice is a layered record. At the base are frozen plains of water ice. Within fractures are salts drawn from depth. Upon the outermost grains are radiation products formed in place. Together they give Europa its distinctive markings and create a bridge between the hidden sea and the space environment. The shell is not an inert wall, but a reactive filter storing altering and passing material between interior and exterior. Though the world looks calm from afar, every patch of colour on its surface is a quiet sign of ongoing chemical change under the influence of tides and radiation. Deep below Europa's ice shell lies a rocky mantle that may host sources of heat beyond tidal flexing alone. Where rock meets water, hydrothermal activity may occur. On Earth, such systems are found along mid-ocean ridges and volcanic seafloor sites, where hot fluids vent into the cold ocean and create steep chemical gradients. These environments support thriving microbial ecosystems that do not rely on sunlight, but instead draw energy from reactions between water and rock. If anything similar exists on Europa, it could provide not only localized warmth, but also ingredients and energy that together build the foundation for habitability. To understand this possibility, one can proceed step by step, beginning with the nature of Europa's interior. Beneath the global ocean lies a mantle made largely of silicate rock, and at its very centre lies a dense metallic core. Heat within the rocky mantle comes from several sources. Radioactive decay of long-lived isotopes releases steady energy. Tidal deformation, though strongest in the ice and ocean above, can also flex the solid rock and release heat. If the ocean rests directly upon rock, that heat can drive circulation of water through fractures and pores, a process known as hydrothermal convection. Water that penetrates downward along cracks becomes warmer, dissolves minerals and rises again when buoyant, carrying dissolved chemicals back into the ocean. On Earth, such systems emerge at vents that release plumes of hot mineral-rich fluid into the sea. Black smokers and white smokers are famous examples. Around them, life flourishes not through photosynthesis, but through chemosynthesis, where microbes use chemical energy from hydrogen, methane, or sulfides. Larger organisms form symbioses with those microbes. The analogy to Europa is not perfect, yet it provides a model. If hydrothermal vents exist on Europa's seafloor, they would provide steady chemical disequilibria that could fuel microbial metabolism. Several lines of reasoning suggest that such activity is possible. Models of Europa's cooling history indicate that significant heat remains within the rocky interior. Meteorite studies of primitive solar system material show that reactions between water and silicate rock naturally produce hydrogen gas. When water circulates through warm rock, it interacts with iron-bearing minerals and undergoes a process called serpentinization. This reaction forms hydrated minerals and releases hydrogen. Hydrogen is a potent fuel for microbes on Earth. If similar reactions occur on Europa, then even without sunlight, the ocean could contain both hydrogen from rock and oxidants from surface chemistry, creating a potential energy system that life could exploit. Seafloor topography also matters. If the ocean is in direct contact with rock, it could host spreading centers, volcanic plains, or mountain-like ridges where hot fluids rise. If high-pressure ice phases intervene between liquid and rock, then direct hydrothermal circulation would be limited or prevented. Estimates of Europa's ocean depth vary, but many models allow for regions where liquid contacts rock. Even a partial connection is enough to create localized hydrothermal circulation and chemical exchange. Evidence for seafloor activity is indirect but suggestive. The detection of induced magnetic fields confirms a salty ocean, and the salinity itself hints at water-rock interaction. The presence of sulfur compounds on the surface suggests that materials cycle between interior and exterior, possibly through hydrothermal leaching of rocks that then contribute solutes to the ocean. Plumes of vapour, when observed, sometimes contain hints of salts, and possibly simple organics which may have been carried upward from depth. None of these observations prove vents exist, but they are consistent with an active seafloor. Hydrothermal systems would influence the chemistry of the entire ocean. Fluids that rise from vents carry reduced compounds such as hydrogen, methane, and sulfides. When these mix with oxidants delivered from the surface, strong chemical gradients form. Such gradients are what microbes on Earth exploit to gain energy. Even in the absence of complex life, these gradients could support microbial communities and maintain a dynamic chemical cycle. Hydrothermal circulation also redistributes heat. Instead of allowing the seafloor to cool uniformly, warm fluids rising through vents can maintain local regions of elevated temperature. This extra heat may prevent parts of the ocean from freezing, even if global balances would otherwise allow it. In this way, vents act as stabilizers that help sustain liquid water over geologic time. The scale of such systems on Europa is difficult to know. On Earth, hydrothermal vent fields are often only kilometers across, yet they can have global impacts on ocean chemistry. If Europa's seafloor hosts even scattered vent systems, their combined effect over millions of years could be significant. By leaching elements from rock, they enrich the ocean with nutrients. By supplying reduced gases, they create energy sources. By releasing heat, they stabilize conditions for liquid water. Laboratory experiments and computer models support the plausibility of these processes. Simulations of water-rock interaction under Europa-like conditions show production of hydrogen and alteration of minerals. Studies of deep-sea organisms on Earth show that life can thrive in total darkness with only chemical energy. While Europa lacks sunlight at depth, it does not lack the fundamental ingredients of water, rock, and heat. The presence of salts on the surface confirms that chemical complexity exists, and the presence of oxidants confirms that energetic compounds are being made. The missing link is the confirmation of hydrothermal circulation, which would tie these ingredients into a cycle. Even without direct observation, one can build a logical sequence. Radioactive decay and tidal heating keep rock warm. Water contacts that rock and react, releasing hydrogen. Warm fluids rise and vent into the ocean. They mix with oxidants and salts. The mixture creates disequilibria that could sustain microbes. Over long timescales, the cycle continues, renewing supplies of both fuel and oxidants. The system is closed in the sense that energy comes from within and from radiation above, but it is open enough to keep chemistry moving. Reflecting on Earth's hydrothermal ecosystems helps illustrate what this means. At mid-ocean ridges, dense clouds of microbes form mats that feed on vent chemistry. Tube worms, clams, and shrimp live in association with those microbes. None of those forms are expected on Europa, but the principle that life can thrive without sunlight holds. Chemosynthesis provides a universal model for energy use in dark oceans. If life ever arose on Europa, hydrothermal vents are among the most promising refuges where it could persist. The implications for habitability are profound, but do not require speculation about outcomes. What is important is that physics and chemistry allow such systems to exist. Water, rock, and heat together naturally make reactive compounds. Those compounds form gradients. Gradients store energy. Energy can power metabolism. The link from geology to potential biology is a chain of small, clear steps. Europa offers conditions where that chain could be complete. While no probe has yet reached the ocean, the reasoning rests on established processes that can be observed and tested on Earth and in laboratory settings. Thus, the idea of hydrothermal vents on Europa is not fantasy, but a careful extrapolation from known science. In the silence beneath the ice, if the ocean touches warm rock, fluids could rise, minerals could alter, gases could form, and energy could flow. These processes would proceed whether or not life uses them, but their presence would mean that one of the necessary foundations of habitability is met. For life as known on Earth to exist, liquid water must be joined by a steady supply of energy. On Europa, several potential energy sources are present, though each comes with limits. Step by step, they can be traced through the interactions of tides, radiation chemistry, and internal circulation. At the most basic level, tidal heating is the engine that sustains the ocean. Jupiter's gravity flexes the ice shell and the interior with each orbit, and mechanical energy is transformed into heat. This heat prevents complete freezing and maintains the balance between liquid and solid. Yet tidal heating by itself only supplies warmth. It does not provide chemical disequilibria that organisms could exploit. For life, energy is not only about temperature, but about the availability of gradients across which chemical reactions can proceed. Radiation at the surface is another important factor. Charged particles trapped in Jupiter's field bombard Europa's ice-splitting water molecules and creating oxidants. Products such as hydrogen peroxide and molecular oxygen are formed and stored in the outermost layers. On their own, these products accumulate in frozen grains. If cracks open, or if surface material is transported downward through slow overturn or foundering, these oxidants can reach the liquid ocean. There they may encounter reduced compounds rising from the seafloor, such as hydrogen or sulfides from hydrothermal reactions. When oxidants meet reductants, chemical energy is released. Microbes on Earth often rely on this kind of gradient, for instance, by using oxygen to oxidize hydrogen or methane. The amount of energy available depends on how efficiently surface products are delivered into the ocean. The ice shell may be tens of kilometers thick, which makes transport difficult. Still, evidence of chaotic terrain and rafts suggests that surface blocks can founder, bringing oxidized material downward. Similarly, briny plumes may vent upward, freeze, and then eventually sink again, returning oxidants to depth. Even if transport is slow over millions of years, it can add up to a significant input. Hydrothermal activity provides another class of energy sources. When water interacts with warm rock, hydrogen and methane can be generated. These are reduced compounds chemically rich in electrons, and they can serve as fuels if oxidants are available. Sulfide minerals can also form and provide further chemical potential. If the ocean floor hosts hydrothermal vents, then local plumes of reduced compounds could rise into the ocean and persist for long distances before mixing. Each vent would be a small chemical factory steadily feeding energy into its surroundings. Together with oxidants from above, they establish a system where opposing fluxes meet. Life on Earth thrives in similar settings at mid-ocean ridges. Europa's ocean, if it has vents, could host similar gradients even without sunlight. Another potential source lies within the ice shell itself. As tidal flexing opens cracks, liquid water can rise and freeze, releasing heat of fusion and concentrating solutes. Salty brines trapped within the shell may experience cycles of freezing and melting, producing small-scale chemical gradients. Radiation products implanted from above can also collect in brines, creating pockets of chemistry that differ from their surroundings. Although these microenvironments are less energetic than vents, they could still matter if life can exploit small niches. It is worth noting that not all energy is beneficial. Radiation at the surface is destructive to organic molecules. Any life exposed directly on the plains would be sterilized quickly. But within the ocean, shielded by kilometers of ice, radiation cannot reach. Instead, radiation becomes a positive factor only if its products are delivered downward. Without transport, surface oxidants remain inaccessible. Thus, the shell is both a barrier and a bridge. It blocks radiation from destroying molecules in the ocean, but also governs how radiation products enter. Models of energy flux attempt to quantify these inputs. Estimates of tidal heating within the ice and oceans suggest global power levels sufficient to keep the ocean liquid for billions of years. Estimates of oxidant production by radiation suggest annual yields that, if delivered fully to the ocean, could rival the energy flux available in Earth's deep ocean ecosystems. Yet the delivery rate is uncertain. If only a small fraction of oxidants reach the ocean, the usable energy falls. If a large fraction descends, then Europa's ocean could be chemically active enough to support simple life. In comparing sources, one finds a complementary pattern. Tidal heating provides thermal stability but little redox chemistry. Radiation provides oxidants but requires transport. Hydrothermal circulation provides reductants but requires contact between water and rock. When combined, the three sources create a complete system. Heat keeps the ocean liquid. Radiation supplies oxidants. Hydrothermal vents supply reductants. Together they establish chemical disequilibria. This triangle of processes is one reason scientists consider Europa among the most promising places to search for extraterrestrial life. Constraints remain important. The thickness of the ice lid limits mixing. If the ocean is capped by high-pressure ices rather than liquid against rock, hydrothermal sources may be suppressed. If oxidants are trapped near the surface, the ocean may be starved of energy. If tidal heating varies with time, the balance of processes may shift. These uncertainties remind us that conditions for life are not guaranteed, only possible. They also guide mission designs because instruments must search for signs that transport chemistry and gradients truly exist as hypothesized. Analogues on Earth help illustrate the plausibility. In Antarctica, subglacial lakes such as Lake Vostok remain liquid beneath kilometers of ice. There, microbes persist using nutrients supplied by rock and trace oxidants. In Earth's deep ocean, hydrothermal vents support rich ecosystems without sunlight. At shallower depths, brines concentrate salts and sustain unique microbial communities. Each of these examples shows that life can exploit small fluxes of energy in dark, isolated settings. Europa shares important similarities, though it also differs in its strong radiation environment and in the uncertainty of its seafloor contact. The study of these analogues gives a grounded basis for considering Europa's habitability. The role of chemical gradients cannot be overstated. Life requires not only matter, but also free energy, meaning molecules in different states that can react. Water and rock alone are chemically close to equilibrium, offering little free energy. Radiation breaks that equilibrium at the surface by splitting water and making oxidants. Rock-water reactions break equilibrium at the seafloor by releasing reduced gases. When these fluxes meet, disequilibria form, and that disequilibria is a potential power source for life. This logic is not speculative, but a direct application of chemistry. The main question is not whether these processes occur, but whether their outputs reach the same place in sufficient quantity. Even without life, the interactions among tidal heating, radiation chemistry, and hydrothermal reactions make Europa a dynamic world. Its ocean is not static, but is influenced by inputs from above and below. Energy moves, compounds circulate, and gradients form. These are the basic ingredients of a habitable environment. If life never arose, the ocean is still chemically alive. If life did arise, then these same processes would help sustain it. In the silence beneath the ice, currents could carry oxidants downward. Vents could deliver reductants upward, and slow mixing could bring them together. There is no need for sudden events or dramatic upheavals. Step by step, cycle by cycle energy would flow in the ocean of a distant moon. When considering whether Europa's hidden ocean could support life, comparisons with Earth's own extreme environments provide guidance. Although conditions on Europa are not identical to any single place on Earth, there are several analogues that help illustrate how organisms can survive without sunlight with limited energy and under kilometers of ice or rock. By looking carefully at these analogues, one step at a time, one can build a cautious picture of how Europa's environment might be understood. The most direct parallel is found in Earth's deep ocean hydrothermal vent communities. At mid-ocean ridges and volcanic seafloor sites, hot fluids rich in hydrogen, sulfides, and methane emerge into cold seawater. Here microbes thrive by chemosynthesis, using chemical reactions instead of light to build organic matter. Larger organisms such as tube worms and clams form symbioses with those microbes. Although Europa lacks sunlight entirely beneath its ice, the principle that chemical energy can support complex ecosystems without photosynthesis is already proven on Earth. It shows that light is not a requirement for life, only one option among many. Another parallel exists in subglacial lakes sealed beneath Antarctica's thick ice sheets. Lake Vostok. Lake Whillans and other hidden bodies of water remain liquid beneath several kilometers of ice due to geothermal heat and pressure. Despite total darkness and isolation for millions of years, microbial life has been detected in these lakes, sustained by nutrients from rock organic material trapped in ice and trace oxidants. The analogy to Europa is close. Both involve liquid water beneath a thick lid of ice protected from radiation and insulated from surface temperature swings. If microbes can persist beneath Antarctic ice, it suggests that a similar mode of survival could be possible beneath Europa's shell, provided chemical inputs are available. Earth's permafrost regions also offer insights. Microbes are found living in frozen soils, where temperatures remain well below freezing most of the year. They persist by entering dormant states, or by maintaining metabolism at extremely low rates. If brine pockets exist within Europa's ice shell, microbes could in theory inhabit those pockets even without access to the deeper ocean. Such niches would be small and scattered, but they demonstrate that life can exploit marginal habitats when energy and liquid water are present even in limited amounts. Deep mines on Earth reveal yet another analogue. Microbes have been discovered living kilometers below the surface, isolated from sunlight and surface ecosystems. These organisms derive energy from reactions between water and minerals, often producing or consuming hydrogen. They show that life can endure in rock-poor spaces supported only by geochemical energy. Europa's rocky mantle, if it interacts directly with its ocean, could provide a similar environment. Even if the main ocean is separated from the rock by layers of high pressure, ice-localized zones of contact might persist where such chemolithotrophic life could exist. Salt brines under cold conditions also support life on Earth. In places like the Don Juan Pond in Antarctica, extremely saline water remains liquid even at very low temperatures. Microbes are able to survive in these hypersaline brines, adapting to osmotic stress. Europa's surface shows evidence of salts, and its ocean likely contains significant salinity. While high salt concentrations can be a challenge, they also prevent freezing and maintain liquid water. The fact that life tolerates such extremes on Earth expands the possible range of habitable niches on Europa. The energy economy of these analogues is modest compared with surface ecosystems that use sunlight yet life persists. It does so by using gradients efficiently, by recycling nutrients, and by surviving with low metabolic rates. This lesson is crucial for Europa. If life exists there, it need not be abundant or rapid. It could be sparse, slow-growing, and confined to microenvironments where conditions align. The mere possibility is important because it demonstrates that the absence of sunlight and the presence of thick ice do not preclude survival. Another analogue comes from temporary plumes and geysers on Earth. In places like Iceland, geysers and hot springs bring subsurface water to the surface briefly. Microbes are often carried upward with the water and survive transport through extreme changes in pressure and temperature. Europa's suspected plumes may perform a similar function, ejecting ocean material through cracks into space. If microbes lived in the ocean, some could in principle be transported upward and frozen into ice grains that then fall back or escape. Studying Earth's geysers helps frame what one might expect in such an environment. Even in Earth's upper atmosphere and in clouds, microbes have been found. These analogues remind us that life can exist in many places where energy is scarce and conditions appear hostile. Europa combines several of these features: deep dark oceans, brine pockets, interaction with rock and exposure to radiation products. It does not replicate any one analogue exactly, but the overlap shows that none of its conditions are beyond the known limits of life. This does not prove that life exists there, but it grounds the idea in observed resilience. Considering energy flow provides a common thread through all analogues. In Earth's hydrothermal vents reduced gases from rock-meat oxidants in water. In subglacial lakes, oxidants from ice mix with reduced minerals from sediments. In deep mines, hydrogen from water-rock reactions sustains microbes. In hypersaline brines, concentration gradients support metabolism. Europa combines similar processes on a global scale. The cycle of oxidants from above and reductants from below is not unique, only relocated to a distant icy moon. Even the role of radiation has an analogue. On Earth's surface, ultraviolet light from the sun splits molecules and drives atmospheric chemistry. On Europa, charged particles from Jupiter perform a similar function in ice. In both cases, external energy sources alter chemistry and create new compounds. In both cases, the results can fuel further reactions that life could exploit. Finally, Europa's ocean is stable over geologic time, much like Earth's deep environments. Stability is critical because life requires not only favourable conditions, but also time to adapt and persist. While Europa's surface is hostile, the ocean beneath kilometres of ice is shielded and could remain liquid for billions of years thanks to tidal heating. This timescale is long enough for complex chemistry to accumulate and for any possible life to sustain itself. The comparisons therefore reveal a pattern. At each step, conditions on Europa resemble conditions where life already exists on Earth, though not perfectly. Hydrothermal vents, subglacial lakes, deep mines, hypersaline brines, and permafrost all provide examples of survival without sunlight and with modest energy. Each example offers a piece of the puzzle. When taken together, they suggest that if Europa's ocean harbours life, it could find ways to endure in forms and modes similar to those seen in Earth's extreme environments. The analogues do not guarantee life, but they remove the argument that Europa is too extreme to allow it. Instead, they frame the ocean as a place where chemistry, energy, and stability coincide in ways familiar to biology on our own world. The idea that Europa could host simple life is grounded in the presence of liquid water energy sources and chemical gradients. If life does exist there, it is most likely microbial, resembling bacteria or archaea on Earth, rather than complex organisms. Step by step, one can examine what form such life might take, how it could function, and what evidence might be left behind. On Earth, microbes dominate environments where energy is scarce, light is absent, and isolation is extreme. In deep ocean vents, they thrive on hydrogen, methane, and sulfides. In subglacial lakes, they live on trace oxidants and organic material. In brine pockets, they tolerate high salt and low temperatures. These examples show that microbes can adapt to nearly any set of conditions, provided liquid water and a source of chemical disequilibrium are present. Europa's ocean fits this model. The environment is dark, sealed beneath ice, and potentially in contact with rock. Radiation products from above and hydrothermal products from below could mix to provide the disequilibria that microbes need. One can imagine cells adapted to cold pressure and chemistry, unlike anything familiar on the surface of Earth. The ocean floor is one likely habitat. If warm vents exist, plumes of reduced chemicals would rise and mix with oxidants. Microbes could gather in these plumes using enzymes to capture energy from reactions between hydrogen and oxygen, or between sulfides and oxidants. Colonies might cling to mineral deposits precipitated from vent fluids, forming biofilms in sheltered crevices. These biofilms would not need light or large energy inputs. They would persist quietly, dividing slowly and recycling nutrients. Similar biofilms are found in Earth's hydrothermal systems, and their fossilized remains can persist as layered mineral textures. If Europa hosts such communities, their traces might be preserved as chemical signatures or as patterns in mineral deposits. The open ocean is another potential habitat. Microbes might drift freely using dissolved nutrients carried by currents. In this case, they would be sparse, spread thinly across the vast volume of water, and their metabolic rates might be extremely low. Still, they could persist for long times by relying on slow but steady fluxes of energy from above and below. The ice-water interface provides another niche. Brainy channels within the lower ice may host communities similar to microbes in Earth's sea ice, where pockets of salt water concentrate nutrients and provide microhabitats. These niches could be especially important for oxidant delivery, because surface products mixed into the ice could be carried downward more easily than into the bulk ocean. Microbes in such settings would need to tolerate cycles of freezing and melting and high salt concentrations. Yet on Earth, many microbes are halophiles that thrive under similar stress. Even the surface, although exposed to radiation, cannot be dismissed entirely. While intense fluxes of charged particles sterilize material, quickly dormant spores or cells embedded in cracks might survive for short periods. Any life from below carried upward in plumes could be briefly present at or near the surface before destruction. Although not a permanent habitat, the surface could serve as a conveyor of evidence, offering samples of material from the ocean that could be studied by spacecraft. The forms of metabolism that Europa's microbes might use depend on the chemistry available. The most promising pathway is hydrogen oxidation, in which microbes combine hydrogen with oxygen to release energy. This requires hydrogen from rock-water reactions and oxygen from radiation products. Sulfide oxidation is another candidate, fueled by sulfides from the sea floor. Methanogenesis, in which carbon dioxide is reduced to methane using hydrogen, is possible if carbon is present in sufficient amounts. Each of these metabolisms is known on Earth and functions without sunlight. The key is disequilibrium, one set of compounds rich in electrons and another set poor in electrons ready to accept them. Life bridges the two and captures energy. The expected complexity of Europa's biosphere is low. Energy fluxes are far smaller than those on Earth's sunlit surface, so biomass would be limited. Growth rates would be slow, cell densities low and ecosystems simple. Life would not build large structures or abundant macroscopic forms. Instead, it would exist primarily at the microbial scale, invisible to the naked eye. This limitation does not make the possibility less significant. Even sparse microbes would demonstrate that life can arise and persist beyond Earth. Evidence for such life would likely be indirect. Plumes venting from cracks could contain organic molecules or cell fragments. Ice grains ejected from plumes and sampled by passing spacecraft might show complex organics or isotopic ratios suggestive of biology. Surface deposits might contain patterns of salts or minerals altered by metabolic processes. In situ, landers could probe the chemistry of ice and search for compounds such as amino acids, lipids, or specific isotopic signatures. Each of these lines of evidence requires cautious interpretation because abiotic processes can mimic some biosignatures. On Earth, the distinction between biological and non-biological chemical signatures can be subtle. Therefore, the search for life on Europa must rely on multiple indicators converging on the same conclusion. If life were discovered, it would raise profound questions about its origin. Did it arise independently in Europa's ocean, showing that life emerges wherever conditions permit? Or was it seeded by transfer from elsewhere, perhaps carried by impacts from comets or meteorites that exchanged material among worlds? These questions cannot be answered without samples, but the presence of microbes alone would already demonstrate that life is not unique to Earth. The possibility of simple life also guides the design of missions. Spacecraft must be sterilized to prevent contamination. Instruments must be sensitive enough to detect faint signals. Sampling must avoid ambiguity. The careful approach reflects how extraordinary the discovery would be. Simple microbes on Europa would be enough to transform our understanding of life in the universe. At the same time, the absence of life would still be informative. It would show that even when water energy and chemistry align, life does not always follow. Either outcome expands knowledge. In thinking about Europa's potential microbes, one can remain calm and precise. No grand declarations are needed. The presence of liquid water beneath ice, of chemical gradients and of energy fluxes are necessary conditions. Microbes are the most likely expression of those conditions if life has arisen. Their forms, metabolisms, and densities are constrained by the limits of energy and by the shielding of ice. They would be small, sparse and slow, but they would be alive. In silence, in darkness, in pressure, they could persist, each cell dividing quietly, each colony maintaining itself across long spans of time. If sampled, their presence would be revealed not by dramatic forms, but by subtle chemical and structural traces. The calm reasoning that leads to this possibility does not claim certainty, only plausibility. Europa may be lifeless, or it may harbour microbial life. Both states are consistent with its known conditions. What matters is that science can outline the possibilities clearly grounded in evidence and analogues, and prepare for the day when exploration provides an answer. For all its potential, Europa also presents severe challenges to the survival of life. These challenges are not dramatic interruptions, but persistent constraints that shape the environment step by step. Each factor can be traced in detail, and together they define the narrow margins within which habitability could exist. The first barrier is the ice shell itself. Estimates place its thickness between several kilometers and several tens of kilometers. Such a barrier makes the transport of nutrients and oxidants from the surface to the ocean slow and uncertain. Without steady delivery of surface products, the ocean might lack sufficient oxidants to balance the reductants from hydrothermal activity. On Earth, the biosphere relies on abundant energy fluxes, but in Europa's case, the flux may be very small. Even if life exists, it could be sparse and energy limited because of this bottleneck. Radiation, while a source of oxidants, is also a destructive force. On the surface, high-energy electrons and ions penetrate the upper layers of ice to depths of several centimeters. Any organic molecules exposed there are rapidly broken apart. This means that Europa's surface is hostile to the persistence of biosignatures. If plumes eject ocean material onto the surface, the chemical traces would be altered within short geological timescales. Searching for direct signs of life at the surface is therefore difficult. Instruments must distinguish between radiation products and original biological molecules, a challenge compounded by the thinness of the altered layer and the limited opportunities for access. Salinity presents another constraint. Observations suggest that Europa's ocean contains significant concentrations of salts. While salts prevent freezing and help maintain liquid water, high concentrations can stress cells by drawing water out of them. Life on Earth includes halophiles organisms that thrive in salt-rich environments, but even these have limits. If Europa's ocean is too saline, the range of possible organisms narrows. The balance between maintaining liquid water and allowing biochemical stability is delicate. Pressure also poses challenges. Europa's ocean, covered by kilometers of ice, lies under pressures far higher than Earth's surface oceans. High pressure affects the stability of biomolecules and the solubility of gases. On Earth, microbes live at depths exceeding 10 kilometers, showing that life can tolerate extreme pressure. Still, the adaptation requires special molecular structures and slow metabolism. If Europa hosts life, it would need to have adapted similarly, which would limit its forms and rates of activity. Another challenge lies in the potential presence of high-pressure ice phases. If the ocean is very deep, layers of dense ice could form at the base, separating liquid water from the rocky mantle. This would reduce or eliminate direct water-rock interactions and suppress hydrothermal circulation. Without such interaction, the supply of reduced compounds would be weaker, and the main source of chemical energy would be cut off. Life could still exist if oxidants reached the ocean from above, but the lack of hydrothermal reductants would make the system poorer in energy overall. The availability of carbon is uncertain. Life as known requires carbon for organic molecules, but the concentration of carbon in Europa's ocean is not well measured. If carbon is scarce, it could limit the complexity and abundance of life, even if water and energy are sufficient. Delivery of carbon-bearing compounds from comets or from interactions with rock may provide some supply, but the total remains unknown. Timescales of stability also matter. Although models suggest that Europa's ocean has persisted for billions of years, its thickness and chemistry may change over time. If heating rates shift due to orbital variations, the ocean could thicken or thin. Periods of reduced heating might freeze much of the ocean, confining water to smaller pockets. Periods of stronger heating could enhance resurfacing, but also destabilize habitats. Life requires long-term stability to adapt and persist. If the environment changes too quickly, it may reset progress repeatedly. Nutrient circulation within the ocean is another factor. On Earth, winds, tides, and currents mix the oceans and redistribute nutrients. On Europa, currents driven by tidal flexing and rotation may exist, but their patterns are uncertain. If mixing is weak, nutrients might accumulate in some places and be depleted in others. Habitats near vents might be rich, while much of the ocean could be poor in energy. In such a case, life would be restricted to small regions and absent elsewhere. Detection poses its own challenge. Even if life exists, it may be sparse and hidden deep below. Sampling a plume or surface deposit might yield ambiguous results, as organic molecules can also be produced by non-biological processes. Without direct access to the ocean, confirming life is extremely difficult. This is a challenge for science, but from the perspective of habitability, it means that life could exist unnoticed, too rare or too deep to reveal itself easily. Considering these constraints in sequence shows how narrow the window for habitability might be. Thick ice hinders transport radiation, destroys surface signatures, high salinity stresses, cells, high pressure, imposes limits, high pressure, ices may cut off rock interaction, carbon may be scarce, stability may vary, and circulation may be uneven. Each factor alone is not decisive, but together they reduce the probability of abundant life. Still, they do not reduce it to zero. Life is known to exist in Earth's most extreme niches, enduring conditions once thought impossible. The possibility remains open that Europa within its margins could support at least microbial communities. It is important to note that these challenges do not imply impossibility. They simply constrain the kinds of life that might be present. Instead of abundant ecosystems, one might expect sparse populations. Instead of rapid metabolism, one might expect slow turnover. Instead of large organisms, one might expect microbes adapted to cold, dark, saline, high-pressure environments. These constraints also help frame what science should look for. If surface deposits are altered by radiation, instruments must look deeper or sample fresher material from plumes. If salinity is high, experiments must test for halophiles. If pressure is extreme, laboratory studies must measure how biomolecules behave under similar conditions. By identifying the constraints carefully, one defines the path forward for exploration. The paradox is that Europa is both promising and limited. It has water energy and chemistry, yet it also has barriers that reduce the likelihood of life. From a scientific perspective, this is valuable. If life is found there, it would demonstrate extraordinary resilience. If life is absent, it would show that even favourable conditions are not enough. Either outcome would be a profound contribution to understanding the nature of habitability. The reasoning remains calm and stepwise. Europa offers a hidden ocean. That ocean may have energy sources. Microbial life could exploit them. But thick ice radiation, salinity pressure, carbon scarcity, stability and circulation all constrain the possibility. What remains is an environment that is not a paradise for life, but a narrow refuge where it might endure if the conditions align. Europa's surface is not simply a frozen lid, but a dynamic interface that may carry clues about the hidden ocean below. The cracked plains, the long ridges, and the occasional plumes all serve as possible windows through which material exchanges occur. By looking closely at these features and considering how they form, one can trace how the ocean might communicate with the surface and how scientists might read those traces. The most direct surface clues come from the network of fractures. These fractures extend for hundreds of kilometers, curving across the plains and intersecting older features. Their symmetry and spacing suggest that they open and close repeatedly under tidal stress. When a fracture opens, even slightly liquid water or slushy brine from depth can be drawn upward. Once near the surface, the water freezes in place, leaving walls of ice that later stand as ridges. The darker material found along many ridges may be frozen brines enriched in salts. These deposits record brief episodes when ocean material was transported upward. Because the cracks cut across older terrains, they represent active processes rather than ancient scars. Each ridge is thus a silent marker of past exchange between ocean and surface. Chaotic terrain provides another line of evidence. In these regions, blocks of ice appear to have broken loose, rotated and then frozen again. The darker, rougher matrix that fills the gaps between blocks may be frozen slush that once intruded from below. The presence of salts and altered ice within these regions supports the idea that liquid reached close to the surface. Some models suggest that pockets of liquid water may temporarily exist within the shell at shallow depths before refreezing. If so, chaotic terrains are snapshots of these transient reservoirs where the ocean briefly communicated upward before being sealed again. Plumes of vapour, though rare and intermittent, are perhaps the most direct sign of exchange. Telescopes have observed faint columns of water vapour rising hundreds of kilometres above the surface. The detections are not consistent. Some attempt to find them, others do not. This inconsistency suggests that plumes are episodic, erupting only under certain conditions. If confirmed, these plumes imply that water from the ocean or from reservoirs within the ice can reach the vacuum of space. As it escapes, it carries with it salts and possibly organic molecules. The material falls back as frost or escapes entirely. For scientists, plumes provide an opportunity. Spacecraft flying through them can directly sample ocean material without drilling. The possibility of plumes has shaped mission planning because it offers a natural pathway for access. Impact craters also provide information. Though rare when they occur, they excavate material from below. Some craters show dark deposits that may represent brines brought upward during the impact. Because craters expose fresher ice, they serve as windows into layers less altered by radiation. Instruments that measure the composition of these fresh exposures can help distinguish between surface radiation products and original salts from the interior. The distribution of colours across the surface adds another clue. Spectral mapping shows that certain ridges and bands are richer in salts than others. This suggests that not all fractures are equal. Some may connect more directly to reservoirs at depth, while others are more superficial. By comparing spectra and mapping, geology scientists can identify locations where ocean material is most likely to have reached the surface. The tenuous atmosphere around Europa is also linked to surface processes. Oxygen detected near the Moon is produced by radiation splitting water molecules in the ice. Hydrogen escapes, leaving oxygen behind. This ongoing outgassing means that surface chemistry is constantly modified, and that some products may diffuse downward or upward. In combination with plume activity, the thin atmosphere reflects continuous interaction between surface and environment. Reading Europa's surface requires caution. Radiation alters compounds quickly, so what is seen is often a mixture of original brines and products of radiolysis. For example, sodium chloride may be altered to take on yellow-brown tones after irradiation. Sulfates may hydrate or dehydrate. Differentiating between these processes requires careful spectroscopy and laboratory experiments to reproduce conditions. Without this work, the true origin of surface features would remain ambiguous. Yet by combining geologic mapping, spectral measurements, and magnetic field data, a consistent picture emerges. Europa's ice shell is active, fractures open and close, brines are transported upward, and plumes may vent ocean material into space. The timescales of these processes are long by human standards but short in geology. A ridge may form over thousands of years, chaotic terrain may evolve over tens of thousands, and plumes may erupt intermittently on timescales of years to decades. This activity means the surface is not a static archive, but a living record of exchange. For astrobiology, these surface clues are critical. They represent the only direct evidence accessible to spacecraft in the near term. If salts, organics, or isotopic signatures linked to life are ever to be found, they are most likely to appear in ridges, chaotic terrains, or plumes where interior material is exposed. For geology, these clues are equally important. They reveal how ice behaves under stress, how thick the shell may be, and how heat and chemistry move through it. The science of Europa depends on reading these subtle signs with precision. The quiet logic can be summarized step by step. Fractures allow brines upward. Ridges and bands record freezing of those brines. Chaotic terrains mark places where blocks floated in slush. Plumes, when present, eject ocean vapor. Impacts expose fresh ice. Spectra reveal salts concentrated along active features. Radiation modifies the surface but does not erase the evidence. Together, these observations show that Europa's ocean and surface are not isolated. They interact even if only intermittently, and those interactions leave behind calm but measurable signs. Europa's surface, therefore, is both a barrier and a window. It blocks direct view of the ocean, yet it carries quiet records of the processes below. By reading those records, scientists can infer the ocean's presence, its chemistry, and even its potential for life. The ground may look calm and simple from afar, but each ridge and stain holds information waiting in silence for careful interpretation. Europa has been visited by several spacecraft, each adding pieces to the understanding of this distant moon. These missions did not drill through ice or sample the ocean directly, but their instruments recorded data that shaped nearly every conclusion about Europa's geology, chemistry, and potential habitability. By following the sequence of missions step by step, one can see how the picture of Europa was built over time. The first close looks came from the Pioneer spacecraft in the early 1970s. These probes flew past Jupiter and returned images that showed Europa as a small, bright world. The resolution was limited, but even then, scientists noticed that its surface lacked many large craters and appeared unusually smooth. This early glimpse suggested that Europa might be geologically active, because an old and inactive surface would have been heavily cratered. Soon after, the Voyager missions provided sharper views in the late 1970s. Their cameras revealed the network of ridges and bands that crisscrossed the plains, the scarcity of impact scars, and the presence of disrupted regions. These observations changed Europa from a pale dot to a world of complex geology. The features did not resemble those of the Moon or Mars, but instead suggested processes unique to ice. Scientists began to consider that a subsurface ocean might exist because fractures and bands seemed easier to explain if ice could move or decouple from deeper layers. In the 1990s, the Galileo spacecraft orbited Jupiter for many years and passed Europa repeatedly. Galileo carried instruments that measured magnetic fields, spectra of surface materials, and high-resolution images. During one flyby, its magnetometer detected an induced magnetic field around Europa. This result was crucial. It indicated the presence of a conducting layer beneath the surface most naturally explained as a salty ocean. The strength and timing of the field matched predictions for a global shell of liquid water lying beneath ice. This evidence transformed the debate from speculation into a supported model. Galileo's spectrometers also detected signatures of hydrated salts and possible sulfur compounds on the surface. These findings reinforced the idea that ocean brines had reached the surface through fractures. Its images mapped chaotic terrains in detail, showing rotated blocks and disrupted ice fields that hinted at liquid reservoirs beneath. Galileo therefore provided not only confirmation of a subsurface ocean, but also evidence for communication between that ocean and the surface. Other instruments on Galileo measured charged particles and detected thin layers of oxygen around Europa. This oxygen was not produced biologically, but by radiation-splitting water molecules in surface ice. The presence of this tenuous atmosphere showed that radiation chemistry was active and that oxidants were continuously generated at the surface. These oxidants might eventually migrate downward and supply energy to the ocean. In the 2000s, the Hubble Space Telescope contributed further clues from afar. Observations in ultraviolet light suggested the presence of plumes of water vapor erupting from Europa's surface. Though not always visible, these plumes, when present, rose hundreds of kilometers above the ground. They provided a possible way for ocean material to reach space directly. Although the detections were intermittent and sometimes debated, the possibility of plumes added great interest because spacecraft could fly through them and sample their contents without drilling. More recently, ground-based telescopes and reanalysis of Galileo data have strengthened the case for plumes. Signals consistent with water vapor have been found on multiple occasions, though always faint. The irregularity of detections suggests that plumes are sporadic, possibly triggered by tidal stress that opens fractures at certain orbital positions. If confirmed, these plumes represent the most accessible path to detecting chemical or biological signs from the ocean. Planned missions will take advantage of this opportunity. The European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, is on its way to the Jovian system. It will study Europa along with Ganymede and Callisto, focusing on ice shell surfaces and environments. Instruments include cameras, spectrometers, and a radar capable of probing beneath the ice. JUICE will not orbit Europa, but will perform multiple flybys gathering detailed data on its geology and composition. Shortly after NASA's Europa Clipper mission will arrive, it is specifically designed to investigate Europa's habitability. Clipper will orbit Jupiter and perform dozens of close flybys of Europa each pass, gathering high-resolution images, radar profiles of the ice shell, thermal measurements, and plasma data. It will also carry a mass spectrometer capable of analyzing the composition of particles in plumes if they are encountered. By combining these instruments, Clipper aims to determine the thickness of the ice, the depth and salinity of the ocean, the chemistry of the surface, and the nature of any plumes. The mission is not intended to land or to drill, but it represents the most ambitious attempt yet to answer whether Europa could support life. The role of spacecraft in shaping understanding cannot be overstated. Without them, Europa would remain a bright point of light. With them, it is now a world with an ocean-active geology, surface chemistry, and possible plumes. Each mission has added layers of evidence, and each has shaped the questions that follow. Instruments sensitive to magnetic fields revealed the ocean. Cameras showed ridges and chaotic terrains. Spectrometers identified salts and radiation products. Telescopes hinted at plumes. Together, these results transformed Europa from a speculation into one of the most promising targets in the search for life. Yet spacecraft also revealed challenges. Radiation levels near Europa are intense, complicating operations. The thick ice makes direct access to the ocean difficult. The surface is altered quickly, making biosignature preservation uncertain. These lessons inform the design of future missions, which must balance ambition with feasibility. Some proposals envision landers that could touch down on Europa's surface, melt or drill into the ice, and analyze samples directly. Such missions face engineering and planetary protection challenges. Others imagine long-term concepts such as probes that could melt through the shell and swim in the ocean. These are far beyond current technology. For now, orbital and flyby missions offer the most realistic path. The role of robotic explorers extends beyond data collection. They test ideas, confirm or reject hypotheses, and refine the models that scientists use to describe Europa. Each new observation is checked against previous knowledge, and contradictions drive further inquiry. The process is cumulative and calm, built not on single discoveries but on careful accumulation of evidence. Step by step, Europa has been revealed by distant instruments, and step by step more will be learned. The knowledge is not complete, but it is coherent. Europa is an icy moon with a global ocean, a fractured surface, salts and oxidants, possible plumes and tidal heating sufficient to keep water liquid. Spacecraft established each part of this picture, and future spacecraft will refine it further. The quiet persistence of exploration continues adding clarity to a world that remains far beyond human reach. Despite the progress made by spacecraft and telescopes, many open questions remain about Europa. Each piece of evidence points toward the existence of a global ocean beneath ice, but the details of that ocean and its potential for life are still uncertain. These uncertainties are not failures but natural outcomes of studying a distant world with limited tools. By setting them out one at a time, one can see clearly what remains unknown, and why these gaps matter. The first major question concerns the thickness of the ice shell. Estimates range from only a few kilometers to more than 30 kilometers. A thinner shell would mean more frequent communication between the ocean and the surface, easier transport of oxidants and nutrients, and a greater chance that plumes connect directly to the ocean. A thicker shell would mean less communication, fewer plumes, and a greater barrier for any future exploration. Current radar and gravity data are not sufficient to resolve this range, so missions like Europa Clipper will attempt to measure it more directly. A second uncertainty lies in the chemistry of the ocean itself. Salts are detected on the surface, but their exact type is debated. Some interpretations favor magnesium sulfate, while others favor sodium chloride. The difference is significant because it points to different interactions between water and rock. If sodium chloride dominates Europa's ocean, may resemble Earth's seawater more closely. If sulfates dominate the chemistry, may be harsher for life. The concentration of carbon, nitrogen, and phosphorus is also unknown. These are essential building blocks for life, but without direct samples, their abundance can only be guessed. A third question concerns the depth and structure of the ocean. How many kilometers of liquid water exist beneath the shell, and does the ocean rest directly on rock, or is it separated by layers of high-pressure ice? If water meets rock, hydrothermal activity is likely providing chemical energy for life. If high-pressure ice lies between, that energy source is reduced. Models allow for both possibilities. Without seismic measurements or direct sampling, the structure remains unresolved. The circulation of the ocean is another open issue. On Earth, currents distribute nutrients and heat across the globe. On Europa, tidal forces and rotation could drive currents, but their strength and pattern are unknown. If circulation is vigorous, oxidants from above and reductants from below could mix widely, creating habitable conditions across the ocean. If circulation is weak, energy might remain localized near vents, and much of the ocean could be chemically poor. The truth will determine whether life, if it exists, would be widespread or confined to small regions. The presence and nature of plumes remain uncertain as well. Some observations detect them, others do not. If plumes exist, do they rise directly from the ocean, or only from shallow reservoirs within the ice? How frequent are they, and what do they contain? These questions are critical because plumes provide the most accessible samples for spacecraft. A single, confirmed detection of complex organic molecules in a plume would transform understanding. But until detections are consistent, their role remains unresolved. The rate at which oxidants from the surface are delivered to the ocean is also not well constrained. Radiation clearly produces oxidants in surface ice, but how much of that material actually reaches the ocean is unknown. If the ice shell is thick and stagnant, the delivery could be minimal. If it overturns or founders, the delivery could be significant. The energy budget of the ocean depends strongly on this flux. Without it, hydrothermal processes alone may not provide enough chemical disequilibrium to support life. Another question concerns the stability of the ocean over time. Tidal heating depends on orbital resonance with Io and Ganymede. If that resonance changes over millions of years, heating could increase or decrease. Has the ocean always been liquid, or has it frozen and melted in cycles? Stability matters because life requires long time spans to develop. If the ocean froze solid for long intervals, habitability would be reduced. If it has remained liquid for billions of years, habitability would be enhanced. The origin of Europa's ocean is itself debated. Was it created early when heat from formation melted internal ice, or did it appear later through long-term heating? If early, the ocean may have existed for most of the Moon's history, giving life more time to arise. If late, the window of opportunity is shorter. The total age of the ocean is therefore an open question with profound implications. The possibility of organic molecules on Europa is another uncertainty. Organic molecules are building blocks for life, but their abundance on Europa is unknown. They could have been delivered by comets or formed in situ through radiation chemistry. So far, no clear detection of complex organics has been made. Their presence or absence is one of the key unknowns that future missions will seek to resolve. Even the rate of geological activity is uncertain. Ridges and chaotic terrains suggest ongoing processes, but the exact timescales are unclear. Do new ridges form every 1,000 years or every million? Is the surface renewed globally or only locally? The answers will reveal how often ocean material is brought upward and whether the surface preserves recent evidence of habitability. Open questions also extend to astrobiology. If life exists, what form would it take? Would it be based on familiar carbon chemistry, or could it use alternative molecules? Would it be confined to microbial scales, or could larger structures arise in some niche? These questions cannot be answered without direct samples, but they guide the search. Instruments must be designed to detect small and ambiguous signals, rather than expecting clear and abundant evidence. Each uncertainty reflects the limits of current observation. From Earth, Europa is a point of light. From orbiters, it is a globe seen in detail, but still only from the outside. Without landing, drilling, or sampling plumes, many questions cannot yet be answered. But each unknown is also a motivation. The thickness of the ice, the chemistry of the ocean, the presence of plumes, the delivery of oxidants, the stability of heating, the abundance of organics, the rate of activity, all are open questions that drive exploration. The method is cautious and cumulative. Observations are collected, models are tested, and uncertainties are defined. The result is not a complete picture, but a framework of knowledge with clear gaps. Step by step, these gaps can be narrowed by new missions. Until then, Europa remains a world known in outline, with details hidden beneath ice waiting for instruments to resolve them. Future missions to Europa are designed to address the uncertainties that remain. The most ambitious among them is NASA's Europa Clipper, scheduled to perform dozens of close flybys. Its payload of instruments reflects the step-by-step logic of the questions scientists hope to answer. High-resolution cameras will map the surface in detail, resolving features only a few meters across. With these images, scientists can study ridges, bands, and chaotic terrains to understand how they form and how recently they have been active. Spectrometers will measure reflected light across many wavelengths, allowing identification of salts, organics, and radiation products. These data will help determine whether surface deposits represent ocean material or products of surface chemistry. A mass spectrometer will directly analyze particles in space around Europa. If plumes are present, this instrument could detect water salts and organic molecules within them. Even if plumes are absent, the spectrometer can study the thin atmosphere of oxygen and hydrogen produced by radiolysis, refining estimates of oxidant flux. A magnetometer will measure variations in Jupiter's magnetic field near Europa. These measurements can be used to infer the conductivity depth and salinity of the ocean building on the discoveries of the Galileo spacecraft. Radar instruments will probe the ice shell, sending radio waves downward and measuring the echoes. These signals will reveal the thickness of the shell, the presence of layers, and the depth of liquid reservoirs within. If water pockets exist only a few kilometers beneath the surface, radar could detect them. Thermal instruments will measure the infrared radiation emitted by the surface. Areas that are warmer than expected may indicate recent activity or shallow reservoirs of liquid water. Plasma instruments will study how charged particles interact with Europa's surface and atmosphere, clarifying how radiation chemistry operates. Each instrument is targeted at one or more of the open questions identified earlier. Together, they will provide a more complete understanding of Europa's structure, chemistry, and potential habitability. The European Space Agency's Jupiter Icy Moons Explorer, or JUICE, will complement these studies. Although its main focus is Ganymede, it will perform multiple flybys of Europa. Its instruments overlap with those of Clipper, including cameras, spectrometers, and radar. By observing Europa from a different platform, JUICE will provide independent measurements that can be compared with Clipper's results. This cooperation ensures that uncertainties are narrowed from multiple directions. Concepts for future landers have also been proposed. A lander would face extreme challenges. Europa's surface is bombarded by radiation. The ice is hard and brittle, and operations must be brief. Still, even a simple lander could scrape surface material, melt a small sample, and analyze it for organic compounds, salts, and isotopic ratios. Such measurements could distinguish between abiotic and possible biological chemistry. Because surface material is altered quickly by radiation landing near a fresh fracture, or recent plume deposit would maximize the chance of success. More distant concepts imagine probes that could melt or drill through the ice to reach the ocean directly. These so-called cryobots would carry instruments through kilometers of ice, then release small submersibles into the water below. Such missions remain far beyond current engineering capability, but they represent the ultimate goal: direct exploration of the ocean itself. Until then, flyby missions remain the practical path. Beyond hardware, mission planning must consider planetary protection. If Europa's ocean is potentially habitable, it is crucial that spacecraft do not introduce Earth microbes. Contamination could alter the environment and confuse the search for life. International protocols require strict sterilization of spacecraft. Instruments must be cleaned, parts baked, and procedures followed to reduce microbial load to the lowest possible level. These precautions add complexity and cost, but are essential to maintain the integrity of exploration. Another consideration is the intense radiation environment near Europa. Spacecraft electronics must be shielded carefully to survive multiple flybys. Instruments must be designed to tolerate damage. Data must be stored and transmitted quickly, because the environment shortens hardware lifetime. These engineering constraints shape the design of missions as much as scientific goals. The expected data from Europa Clipper and JUICE will refine nearly every aspect of Europa's story. The thickness of the ice shell, the chemistry of the surface, the presence or absence of shallow reservoirs, the properties of the ocean, and the composition of the tenuous atmosphere will all be constrained. Even if life is not detected, the data will determine whether the ocean is truly habitable. Scientists will know whether oxidants are delivered downward, whether reductants are supplied upward, whether the energy budget is sufficient, and whether chemistry is favorable. The process is incremental but decisive. Each answer builds upon the last. Step by step, exploration moves from broad outlines to sharper details. In planning these missions, scientists also consider what signs of life could be detectable. Direct imaging of cells is unlikely. Instead, instruments will search for chemical biosignatures. These include complex organic molecules such as amino acids and lipids patterns in isotopic ratios that indicate biological processing, and specific combinations of compounds that are hard to explain abiotically. The detection of such signals in plumes or surface deposits would not prove life on its own, but multiple consistent signals would strengthen the case. Designing instruments sensitive enough to detect faint traces is one of the key challenges of mission planning. The search for life on Europa is not isolated. Other icy moons, such as Enceladus at Saturn, also show plumes and oceans. Comparing them will help distinguish what is unique about Europa and what is common among icy worlds. In this way, missions to Europa contribute not only to the study of one moon, but to the broader question of habitability across the outer solar system. The stepwise logic is clear. Spacecraft confirm an ocean. Instruments measure ice thickness. Plumes, if sampled, reveal chemistry. Surface deposits show communication with depth. Magnetometers constrain salinity. Spectrometers search for organics. Radar detects layers. Thermal sensors find hotspots. Each step narrows uncertainties and guides the next. In the quiet persistence of exploration, Europa is being transformed from a mystery into a world understood in detail. The promise of future missions is not drama, but clarity. By gathering precise data, they will answer whether Europa's ocean is habitable, and perhaps even whether it is inhabited. The outcome, whatever it is, will be based not on speculation, but on careful measurement. Europa orbits Jupiter in silence, yet it continues to inspire questions that extend beyond the reach of current missions. While evidence points strongly toward a global ocean, the exact character of that ocean, and the possibility of life within it, remain unsettled. Reflecting on these open questions highlights the depth of what is known and the breadth of what is not. One area of uncertainty concerns the true thickness of the ice shell. Models suggest a range from a few kilometers to more than 30 kilometers, but until radar and gravity data from future spacecraft are collected, the number cannot be fixed. If the shell is thin, surface fractures may connect more easily with the ocean, and plumes may represent direct conduits. If the shell is thick, the ocean may be isolated for long spans and exchanges may be rare. The difference has profound consequences for habitability, yet both possibilities remain consistent with current observations. Another unresolved question is the detailed chemistry of the ocean. The presence of salts on the surface proves that dissolved minerals exist, but whether sodium chloride or magnesium sulfate dominates is unclear. Each possibility points to a different history of water-rock interaction. Sodium chloride would suggest leaching of crustal rock similar to Earth's ocean formation, while magnesium sulfate would suggest more extensive alteration by sulfur-rich materials. The supply of carbon, nitrogen, and phosphorus is even less certain. Without these elements, life as known could not assemble complex molecules, and their abundance is one of the largest unknowns. The stability of the ocean over geologic time is another puzzle. Tidal heating depends on Europa's orbital resonance with Io and Ganymede. That resonance has likely endured for long spans, but its exact history is uncertain. If heating has varied, the ocean may have frozen partly or entirely during some intervals. For life to persist, the ocean must remain liquid for billions of years. Whether this stability has been maintained is a matter for models, not direct observation. The role of high-pressure ice phases remains open. If the ocean is shallow, liquid water could rest directly on rock, promoting hydrothermal circulation and strong chemical gradients. If the ocean is deep, dense ice phases may form at the base, separating water from rock and suppressing interaction. In that case, the supply of reductants would be smaller, and the ocean's habitability reduced. Determining whether the ocean floor is rock or high-pressure ice is critical, but currently beyond the reach of available data. The frequency and nature of plumes is another key uncertainty. Some telescopes report detections, others do not. If plumes are rare, they may not provide regular access to ocean material. If plumes are common, they are the best chance to sample ocean chemistry directly. The difference between shallow reservoirs venting briefly and deep conduits tapping the global ocean is also unresolved. Spacecraft measurements will attempt to settle this by repeated observations. The rate at which oxidants are delivered from the surface to the ocean is unknown. Radiation produces large amounts of oxidants in the upper layers of ice, but how much reaches depth is unclear. If overturn is efficient, the flux could be significant, supporting a chemically active ocean. If overturn is slow, the flux could be minimal, limiting energy for life. This parameter largely determines whether the ocean is habitable or sterile. Organic molecules have not yet been confirmed on Europa. Their presence would not prove life, but would demonstrate that building blocks are available. Their absence would make life less likely, though not impossible. Detecting organics is difficult because radiation destroys them quickly at the surface. Only by sampling fresh deposits or plumes can this question be answered. The circulation of the ocean itself is uncertain. On Earth, currents distribute heat and nutrients globally. On Europa, tides may drive currents, but whether they are strong enough to mix oxidants and reductants widely is not known. If circulation is weak, life may be confined to narrow habitats near vents. If circulation is strong, life could be more widespread. The presence or absence of life remains the greatest question. If life exists, is it limited to microbes, or could more complex structures have arisen? Energy constraints suggest microbes are most likely, but without sampling, this cannot be known. If life does not exist, the reason may be the absence of one crucial ingredient, perhaps carbon or efficient energy flux. The answer awaits exploration. These uncertainties define the frontier of knowledge. They are not signs of weakness in understanding, but reflections of the limits of distant observation. Each open question is a target for missions, a point where new instruments can add clarity. Step by step, the list of unknowns will shrink as data are gathered. For now, Europa remains a world of possibilities neither confirmed nor dismissed. The calm logic is simple. A global ocean almost certainly exists. Energy sources almost certainly exist. Chemistry is active. Communication between surface and ocean is likely but not yet fully measured. Life is possible, but not proven. Within these boundaries lies the current state of knowledge. The next decade of exploration will test each uncertainty with precise instruments. Whether life is found or not, the answers will refine what is meant by habitability in the outer solar system. Europa remains one of the most compelling targets because it combines water energy and chemistry in a stable environment shielded by ice. These conditions are rare and valuable. The remaining uncertainties keep the story open, waiting for the quiet persistence of science to resolve it.